To escape Earth's gravity, a spacecraft relies on millions of pounds of explosive thrust, but coming back poses a completely different physical challenge. The return trip requires surviving temperatures half as hot as the sun, relying entirely on a heat shield to keep the crew from burning alive. Getting into space requires an enormous amount of kinetic energy. To break the sheer physical grip of Earth's gravity, a rocket has to accelerate an incredibly heavy payload against the constant downward pull of the planet. NASA's solution for the upcoming Artemis mission is the Space Launch System, or SLS. It is the largest, most powerful rocket currently built to overcome that gravitational barrier. At ignition, 4 RS-25 engines and 2 massive solid rocket boosters light up the pad. Together, they unleash 8.8 million pounds of thrust, physically tearing the rocket upward through the atmosphere. But a rocket cannot afford to carry dead weight into space. Within 2 minutes, the side boosters burn out, detach, and fall into the Atlantic Ocean. The core stage follows shortly after, leaving only the Orion crew capsule and the upper stage to push into orbit. Commercial rockets built for low Earth orbit approach this physics problem with a focus on redundancy. A SpaceX Falcon 9 relies on a cluster of 9 smaller Merlin engines. If one fails during ascent, the remaining engines automatically adjust to keep the rocket on its correct path. Whether aiming for the Moon or the International Space Station, escaping Earth comes down to riding a controlled, violent chemical detonation just long enough to reach the vacuum of space. Once a spacecraft reaches that vacuum, the rules of navigation completely change. The sheer brute force of a launch pad ignition is replaced by orbital mechanics, where short, precisely calculated thruster burns manage the vehicle's momentum. This map shows the translunar injection for Artemis 2. The upper stage fires, accelerating Orion to 24,000 miles per hour to break Earth's grip. Instead of the traditional orbit, Orion uses a free return trajectory, utilizing lunar gravity to slingshot perfectly back to Earth. Closer to home, in low Earth orbit, the navigational objective is completely different. Reaching the International Space Station means intercepting a target moving at 17,500 miles per hour and matching its speed exactly. For a commercial vehicle like SpaceX's Crew Dragon, this requires an autonomous phasing process. The spacecraft executes a series of tiny, precise engine burns over several days, slowly lowering and aligning its altitude to match the space station's docking port. This delicate synchronization is incredibly vulnerable to hardware issues. During a recent Boeing Starliner mission, an unexpected loss of helium gas crippled several thrusters in its reaction control system. Because helium is required to pressurize the propellant lines, losing it makes maneuvering in all 6 directions nearly impossible. Navigating the transit phase requires complete trust in autonomous software and fluid dynamics. A minor thruster failure out here dictates whether a mission ends in a secure docking, an endless drift, or a catastrophic collision. To get home safely, a capsule faces its deadliest test. It must instantly shed all of its accumulated orbital velocity, dropping from over 17,500 miles per hour down to 0, without crushing the astronauts inside or tearing itself apart. The capsule slams into the upper atmosphere at Mach 32. At these speeds, the air in front of the vehicle cannot move out of the way fast enough. The intense friction violently compresses the air, creating a shockwave of superheated plasma around the spacecraft. That friction subjects the outside of the Orion capsule to temperatures nearing 5,000 degrees Fahrenheit, which is roughly half the temperature of the sun's surface. The crew survives solely because of the ablative heat shield strapped to the bottom, which absorbs and slowly burns away the extreme heat. Once the capsule survives the worst of the plasma wake, it begins a violent deceleration sequence. A series of thick, stabilizing parachutes aggressively deploy into the rushing air, rapidly slowing the craft to a gentle speed before it splashes into the ocean. However, not all spacecraft rely on water recoveries. The Boeing Starliner is engineered specifically to land on solid ground. That hard landing presents a massive engineering hurdle. Fully fueled, the Starliner weighs nearly 44,000 pounds, roughly the equivalent of 27 school buses. To drop that much mass onto hard desert dirt without injuring the crew, the capsule must fire off a precisely timed array of heavy-duty airbags in the final seconds of its descent. Whether it splashes down in the Pacific Ocean or bounces onto a dry lake bed, bringing the crew back from the void requires threading a needle through the unforgiving laws of thermodynamics and gravity.